Thank you for the introduction. So this is counting martingales for measure and dimension and complexity classes. This is joint work with Adewale, Sekoni, and Hadi, Shafei. So in this talk, we'll combine resource-bounded measure and dimension with counting complexity and apply it to circuit complexity and quantum complexity. So I'll begin by giving a little bit of motivation and background for why we're doing this. So resource-bounded measure is an effective version of Lebesgue measure. It's introduced by Jack Lutz in 1992 to measure the size of complexity classes. Later on, Jack Lutz also introduced resource-bounded dimension as an effective version of Hausdorff dimension, which is one of the most commonly used fractal dimensions. Both of these are defined using martingales that are computable within a resource bound. So the most commonly used resource bounds are polynomial time and polynomial space. Polynomial time martingales define P major and P dimension, and those work for measuring complexity classes within exponential time. P space martingales define P space measure and P space dimension, which works inside exponential space. But there's a lot of complexity between P and P space, and there's many open questions for intermediate classes. And so we need finer grained tools to measure things between P and P space. So the tool we introduce, our main conceptual contribution is counting martingales. So these are martingales that will be defined using functions from the counting complexity classes sharp P, span P, or gap P. And using these, we define resource-bounded counting measures and counting dimensions that lie between polynomial time and polynomial space measures and dimensions in terms of their relative strength. We show that many martingale constructions in the literature can actually be viewed as counting in disguise. And then, as I mentioned, we're going to use these new tools to address circuit complexity and quantum complexity. So what is a martingale? So a martingale is a function mapping strings to non-negative real numbers that satisfies this averaging condition here. We view a martingale as acting on Cantor space, the infinite binary tree. And so here's the initial part of the tree. And you can see that every node is the average of the two nodes immediately below it. That's the martingale property. So we use martingales to try to measure complexity classes. So we have to encode decision problems and complexity classes in Cantor space. And so the way that's done is you take a decision problem, A, a subset of 0, 1 star, and you write down its infinite binary characteristic sequence. So list all the binary strings in the standard order, starting with the empty string, the strings of length 1, the strings of length 2, and so on. And for each string, you just give the decision bit for A. Does that string belong to A or not? So each decision problem becomes a path through Cantor space, and each complexity class is now a subset of Cantor space. So what a martingale tries to do is it's given a prefix, a finite prefix of a language A, of its characteristic sequence formally, and it attempts to bet on or predict the membership of the next string. So it knows the membership of the first n strings, and it wants to predict the membership of the n plus first string. So the goal of a martingale is to be able to predict complexity classes well. And what it looks like is obtaining large values on every member of a complexity class. But as you can see with the averaging condition here, whatever value you start out with at the root, you have the same average across any level of the tree. So it's difficult to attain large values. If you attain large values somewhere, you have to have very small values or even 0 elsewhere when you do that. So formally, we say that a martingale succeeds on an element of Cantor space if it gets above every constant eventually. Old theorem of Ville in 1939 characterized Lebesgue measure zero sets using martingales. So a class X has Lebesgue measure zero if and only if there's a martingale that succeeds on every member of the class. And resource-bounded measure was introduced by taking the martingales in Ville's theorem and making them computable within some complexity bound. So for P or P space, we can talk about P measure zero or P space measure zero if you have a martingale of that complexity that succeeds on every member of the class. Resource-bounded dimension is defined similarly. You have a stronger notion of success here. So for a number S between 0 and 1, say a martingale S succeeds on an element of counter space if it infinitely often gets above this exponential growth rate. So the smaller S is, the harder it is to do that. Lutz proved that the Hausdorff dimension of a class is the infimum S, where you have a martingale that S succeeds on every member of the class. And he defined a resource-bounded dimension by taking the martingales in that theorem and putting complexity constraints on them, just like for resource-bounded measure. So P martingales give us polynomial time dimension, and P space martingales give us P space dimension. So here's an example of a martingale that we'd like to build. So in this picture here, this blue cone is meant to represent the full binary tree of depth 2 to the n. So each path through the tree is the characteristic string of some Boolean function on n bits. And what we'd like to do is show that the class of problems with small circuits has measure zero or small dimension. So imagine these red nodes here on the bottom are the ones that have small circuits. So there's only a small number of leaves with small circuits. So what we're going to do is work with the minimum circuit size problem. So let's fix a size bound S. You can think of it as 2 to the n over n for the moment. We'll push it up a little bit further later on. But define MCSPS to be the set of all paths through this tree that have an S of n size circuit. And then the way we can define a martingale is using this conditional probability. So you're given some finite prefix, or some string W that's a prefix of in this tree. And you want to compute the conditional probability that when you randomly extend W, it'll have a small circuit. So that's the main computational problem here. If you can, given W, you can compute how many extensions have a small circuit. You can build a martingale and get a resource-bounded measure or dimension result. So Lutz, when he introduced resource-bounded measure and dimension, showed that you can do this in polynomial space by brute force enumerating circuits and counting how many extensions have small circuits. But this is more naturally a counting problem, and it's what motivated us to introduce counting martingales. So let me briefly review some notions from counting complexity that we'll use. Sharp P is probably the most well-known counting complexity class. It simply counts the number of accepting paths of a probabilistic polynomial time Turing machine. Span P is maybe less known. So here you have a Turing machine, and on each path, it can output a string or it can output nothing. And what the function counts is the number of distinct outputs of the machine. So if it outputs the same string on multiple paths, we only count it once. That's a span P function. It counts the span or the size of the set of outputs. And then gap P, you have a PPTM as well, but you're looking at the difference between the number of accepting paths and the number of rejecting paths in the machine. Equivalently, it's the closure of sharp P under subtraction. So those are all function classes, and one decision class we'll use is the class SPP. And the problems in SPP, if its characteristic function is in gap P. So when x is an A, the gap is 1, and when x is not an A, the gap is 0. So here's a picture of how these complexity classes fit together. These are most of the classes I'll use in this talk. So the ones in yellow are counting complexity classes. And so, they generally lie between polynomial time and polynomial space in either the function setting or the decision problem setting. And in the decision problem setting, counting complexity kind of provides a layer between polynomial time and polynomial space that captures a lot of complexity. By Toda's theorem, the polynomial time hierarchy reduces to counting complexity, and randomized and quantum algorithms can be turned into counting complexity as well. And two important facts. Sharp P is equal to span P if and only if UP equals NP. It's a result of Cobbler, Schenning, and Tram when they introduced span P. And they also showed that span P can be approximately counted if you have a pH oracle, specifically in polynomial time with a sigma 2 oracle, or in randomized polynomial time with an NP oracle. So now we're ready to define counting martingales. This is our main concept. So what we do is we just take the ratio of a function from a counting class, either sharp P, span P, or gap P, and divide it by a polynomial time function that, for technical reasons, is always going to be a power of 2. So a sharp P martingale is the ratio of a sharp P function and an FP function, and similarly for span P and gap P. And we can define counting measures and counting dimensions in the same way Lutz defined resource-bounded measure and dimension. So we say that a class has sharp P measure 0 if there's a sharp P martingale that succeeds in every member of the class, and similarly for gap P and span P. So here's the chain of implications that you get showing the relative strength of these things. So this is P measure 0 implies sharp P measure 0, which implies both gap P measure 0 and span P measure 0, which both imply P space measure 0, which implies Lebesgue measure 0. And just as gap P and span P appear to be incomparable, we don't have any relationship between gap P measure and span P measure at this time. So counting dimensions are defined in the same way. We just plug in our counting martingales into the definition of resource-bounded dimension, and you get sharp P dimension is at most the polynomial time dimension, and gap P and span P dimension are at most sharp P dimension, which are lower bound by P space dimension and Hausdorff dimension. So our paper is centered around 5 martingale constructions, 5 counting martingale constructions that are based on ideas from the literature, and we give a number of applications for them. For interest of time, I'll just focus on the first 3 in this talk. So the first one is called the cover martingale construction. So this is the circuit complexity example we were looking at earlier on is a particular instance of this. So here you have, so imagine you have some covering set A. It's a subset of 0, 1 to the n. We'll fix n for now. And define a martingale using this conditional probability. So, so given a string W, you want to compute the conditional probability when you randomly extend it to full depth that it belongs to the covering set. So in this diagram, the green nodes are the ones that belong to A. So what we show is that if the cover set belongs to P or even to UP, you get a sharp P martingale. If the cover belongs to NP, like for example, the minimum circuit size problem, then you get a span P martingale. And if the cover is an SPP, you get a gap P martingale. So let's return to this construction here for circuit complexity and revisit this computational problem. So Lutz, brute force solved this in polynomial space. What we can see is that it's actually a span P function. So we can get a span P martingale here. So given a prefix W, what you do to show this is in span P, you guess an extension X of W and a circuit for it. And then you just compute the truth table of that circuit. And if it's equal to X, then you print X. So if X has a small circuit, generally it's going to have multiple small circuits. This way we'll only count each X one time. And so using that, we're able to sharpen the previous results. This gets into the Shannon-Lupinoff bound. So Shannon famously showed in 1949 that most functions require circuits of size nearly 2 to the n over n. And Lupinoff came in later with a nearly matching upper bound, 2 to the n over n plus times 1 plus order 1 over square root of n. Lutz, when he introduced resource-bounded measure, improved Shannon's lower bound in 2 ways. He boosted it above 2 to the n over n to this 1 plus alpha log n over n factor, where alpha is any number less than 1, which might seem kind of big, but there's this complementary result of Franzen and Milterson showing that every function has a circuit of size not much bigger than that. There's actually an interesting technical gap here between here alpha is less than 1 and here alpha is bigger than 3. It's an open problem to close the gap between 1 and 3 there. We're able to take Lutz's p-space result and turn it into a span P measure result using the cover martingale construction that we just discussed. And then if you apply the fact that span P functions can be approximately counted with the pH oracle, you get that Lutz's lower bound holds within the 3rd level of the exponential time hierarchy. And if you assume a de-randomization hypothesis, say enough to de-randomize BPP to the NP, then this same lower bound holds within the 2nd level of the hierarchy, within E to the NP. So our second martingale construction is called the conditional expectation martingale. You can view it as a generalization of the cover martingale construction, where instead of just having 0s and 1s at the bottom of the tree, now we can have arbitrary function values. And what we're taking is the conditional expectation. So given some prefix in the tree, compute the conditional expectation of the function that you have below it. And so if f belongs to sharp P, you get a sharp P martingale. And similarly for span P and gap P, you get span P martingale or gap P martingale. So an application of this is to improve the dimension of this circuit size complexity class. So here alpha is a real number between 0 and 1. Lutz showed that the class size alpha 2 to the n over n has p-space dimension alpha. Using the cover martingale idea, it's easy to improve this to span P dimension alpha. But in the paper, we use Kolmogorov complexity plus the conditional expectation martingale construction to actually improve that to sharp P dimension alpha, a bit sharper result. Our third martingale construction is called the acceptance probability martingale. And so here you have a probabilistic Turing machine or a quantum Turing machine. And in this example, the acceptance probability is 3/4. And the initial prefix of the language that we're trying to bet on is in the green nodes here. So it starts out 0, 1, 0, 1. But what you do is you just multiply the acceptance probabilities that you have along the path to the node that you're looking at, and multiply that times 2 to the n, and that will give you a martingale as well. And this naturally leads to martingales that succeed on BPP or BQP. A bit more specifically, so Lutz showed that for any constant C, the d time 2 to the Cn class has p dimension 0. So this is a slice of exponential time. We extend that and show that BP time 2 to the Cn has sharp p dimension 0, which of course implies as a special case that BPP has sharp p dimension 0. We're also able to address quantum complexity when we use gap p martingales. And this is because of a nice result of Fortnow and Rogers that acceptance probabilities of quantum algorithms can be gap p functions. It's the result. BQP is contained in AWPP, if you're familiar with that. But we show for any constant C, BQ time 2 to the Cn has gap p dimension 0. And then we also look at quantum circuits. So BQ size little o 2 to the n over n has gap p dimension 0, which implies BQP/Pauli has gap p dimension 0. So one open question, I'll have a few more open questions at the end of the talk, is can we improve the classical advice here from BQP/Pauli to quantum advice, BQP/Q Pauli? I think this is an interesting open problem. Can you give a gap p martingale for quantum advice? So to summarize our main results, counting measures are useful when the p-space measure of a complexity class is known, but its p measure is unknown. So that's the case for all these classes on this slide. So we talked about randomized and quantum algorithms. We talked about circuit size complexity. We have a measure result in the span p setting and a dimension result in the sharp p setting. And then for quantum circuits, we have this little o 2 to the n over n class has gap p dimension 0. Another open problem is to get a result like this one for something like BQ size alpha 2 to the n over n. But as far as we can tell, that class depends on the choice of universal gate set that you use. So there had to be some care to be able to resolve that question. So to sum up, we introduced counting martingales using sharp p, span p, and gap p functions. These are useful if we know the p-space measure of a class, but not its p-bounded measure. We use this to strengthen some results about circuit complexity, and for the first time address quantum complexity with resource-bounded measure and dimension. And I'll just conclude with a few open problems. We wonder if UP has sharp p measure 0, does NP have span p measure 0, and does SPP have gap p measure 0? We can show for each of these first three questions that singletons do. So if you take a singleton in UP, you can build a sharp p martingale that succeeds on it. And similarly for 2 and 3. But the difficulty is doing it uniformly over the whole class. I think it's also interesting to look at the counting measures and dimensions of other counting complexity classes like PP and parity P. And then there's also the question about BQP/Q Pauli. Thank you.